Hello, my name is Justin, one of the members of Group 6. On behalf of my groupmates Li Che and Xian Meng, I'll be here today to present our machine learning project on American Express default prediction. So here are the project objectives. We are supposed to predict the likelihood of credit default for a given American Express customer. We have to build a complete machine learning pipeline using the real-world data that they provide us. And we're supposed to evaluate the performance of our model based on other competitors on the leaderboard. So the key components for this project would include data pre-processing, feature engineering, a lot of model experimentation, as well as evaluation for our ensemble model. So I'll get to that later. For now, I also want to mention that each customer represented by a customer ID is not unique, and that multiple transactions, multiple records of the same customer ID is possible. Now, I said that the data was anonymized, and here is where we key it in. When the features are obfuscated completely, meaning that we are unable to derive form of meaning or importance from the columns at all. This presented a few challenges for us. Firstly, that it had high dimensionality, so it had close to about 190 features alone without any form of feature engineering. It was memory intensive because there were hundreds of thousands of rows that we had to process. The column names could give zero domain clues as to what was more important and what was less important, which meant that we had no idea what features to prioritize during model training. And lastly, because each customer potentially could have multiple records, it required aggregation because the model trains on a row level basis. And so, in order to account for this, we aggregate each customer into a single customer ID and we aggregate all the values associated with all the transactions from that customer ID. I'll get into it more later down the line. So here is our team workflow strategy. We adopted an independent and collaborative workflow. So what this meant was that each member was given the liberty to work and experiment on their own models and pipelines independently. And it was just free reign on whatever the member wanted to do. And we would share our findings and whatever blockers that we had on the way. Afterwards, we would come together to compare our results and we integrated the best performing approaches, the best practices that we found into our final solution. This was kind of a divide and conquer strategy where we could explore as much possibilities as possible within the given time constraint that we had, and it allowed for diverse insights and stronger model selection. So here are our member contributions. So firstly, for Xian Meng, he was responsible for developing supervised classification models. He was focused on optimizing the model accuracy, which led to him designing the final ensemble model that we are using in our final solution. Next, for Li Che, he implemented regression-based models. He performed a lot of hyperparameter tuning for these models and analyzed the relationships between the features. And finally, he assisted with integrating regression output into the ensemble model that we used. And lastly, for me, I was mainly in charge of feature engineering, data processing, and transformation. Kind of models and what rate yielded the best score for us. So here are the challenges that we faced. Firstly, the most apparent challenge that we faced was storage limitation, which meant that for all of us, our local laptop storage was insufficient to hold all that data. This also meant that we were unable to utilize cloud-based platforms like Google Colab, which was the reason why we took a rather unique approach in our workflow style. Other than that solution, the main solution that we took to allow for us to even store the dataset was to move to our own individual desktops instead of laptops and to just do some spring cleaning on our ends so that we're able to accommodate the large dataset. Secondly, we ran into an issue with limited RAM. As the member in charge of feature engineering, this was a problem that I encountered personally, where pandas was too intensive in handling the full dataset. So this solution that we came across was to use chunking or batch processing with the Dask or Polars libraries that include lazy loading. So thirdly, there were obfuscated column names. So these column names were intentionally anonymized to prevent competitors from deriving any form of importance through various ways like domain knowledge. The solution was to aggregate and treat columns equally. Now, lastly, this was our first experience with real machine learning data. It was noisy, it was large, and it was rather inconsistent. And we just required lots of experimentation and trial and error and research to get to the point that we are comfortable enough to work on such a dataset that we've not seen before. So now we get to the pre-processing and feature engineering portion. We took a chunk-wise approach to the loading of data. We'll perform our respective aggregation on that chunk. We had to handle missing values, although in some cases, the models would natively support the handling of missing values. And lastly, for categorical features, we had to encode them so that the models will be able to train on them. So why aggregation? Because each customer may have multiple entries and our machine learning models required single row representation. So this was a way to capture behavior patterns as opposed to concrete values themselves. Moving on to the model development, these were what we tested. We tested gradient boosting models like GBM, XGBoost, CatBoost. And for regression models that were explored by Licha, they offer additional perspective on the variable interaction and the perspective on whether we should go forward using regression models or classification models. Then lastly, we have our ensemble strategy, which is using weighted average. I will get to how we assign the weight and what we would have done differently later on in the presentation. So now we are talking about the handling of large data. And it can be very simply summarized into one line. It was about working around hardware bottlenecks. So why did we need to do this in the first place? It was to ensure that our systems could handle the training and processing of data without any issues like crashing. So what measures am I talking about? Firstly, we used libraries that supported lazy loading, such as Dask or Polars, with chunking to ensure that our RAM usage never gets out of control. And opting for GPU alternatives where possible. This is mainly for the model training portion. So here is an experimental study on the effectiveness of our solution and why it works. So over here is a prediction that I submitted before we implemented a lot of the measures that are present in our final solution. So as you can see, our score was only 0.59. So what was this solution missing? Firstly, it lacked any form of feature engineering. There was no aggregation whatsoever, which brings me to my next point, the probability aggregation. So because the test data allowed for the same customer to make multiple records, while the prediction that we had to submit only accepted one customer per row, I had to aggregate the probabilities from all the rows from that customer ID to give a single prediction per customer, which was the completely wrong approach. Now, one last thing I would like to highlight is that this used only a single XGBoost classifier. So now, with this in comparison, let me show you our final result. Our final submission results are as shown. We obtained the public score of 0.79, which would rank us among the top 67.8% of competitors, so within the top 70% bracket. Now, even though our rank was lower than what we expected, we as a group are proud of what we have achieved given our relative inexperience and time constraints amongst very tight competition. So now is the portion where I talk about what we could have done better going forward had we more capacity and time. So firstly, I mentioned that each column was obfuscated intentionally, so we could not figure out which feature had more or less importance in the prediction accuracy. The best approach would be feature selection with weighting. So this would have been a better approach in terms of knowing which columns were more important in predicting the final probability. Next, we would prefer to have had more models for the ensemble. And lastly, ensemble weighting assignment. So for our final approach, we actually assign the weights for the ensemble manually. Had we done a dynamic assignment of the model weights based on performance, it would have helped in maximizing the score and accuracy of our model as opposed to the manual assignment that was done. So lastly, what did we learn? We learned that large data not only requires just model training, but also feature engineering. And that feature engineering is often as important as the model itself. We learned that ensemble models improve on robustness by reducing the biasness that could have been due to overfitting. And lastly, that machine learning projects involve significant amounts of debugging and tons of iterations to be done right. So in conclusion, we now have a taste of what real-world handling of messy and large datasets is like. Now, we are not saying that this is what a large dataset in the real world would look like, but it is a leap from what we are normally used to. We were exposed to more advanced machine learning workflows, the better practical understanding of what feature engineering is, and lastly, we had hands-on model experimentation and ensemble creation. So with that, I would like to close by saying that despite all the challenges and time constraints that we faced during this project, we successfully achieved our goal of placing within a respectable percentile of the competition, and we also gained meaningful insights into the practical uses of data science. So I'm Justin. On behalf of Group 6 members, Li Che and Xian Meng, thank you for your attention.